and experiences a Lorentz force. This force is called a Lorentz force, and it has the form given there, where F is the force, and we are considering the cross product on R3. So usually for the physicians, the B is the magnetic field, okay? And the law of Gauss says that divergence of B should be 0. So in the most general setting of Riemannian manifolds, we generalize this to motivate the equations of the form we have here, nabla gamma prime equals F acting on gamma prime, where F is the skew-symmetric tensor of type 1, in the tangent space Tm, and here the Gauss law will be traduced in a condition on the associated two form for F. Well, here we make use of the metric, so the two form is associated to the 1 tensor, which is skew-symmetric, and the Gauss of law is equivalent to asking that the two form being closed. Okay, so the definition is the following. So Lorentz force will be on a Riemannian manifold, a tensor field of type 1, which is skew-symmetric and such that the corresponding two form is closed, or we could speak about magnetic field as a closed two form on M. And the magnetic trajectory will be a curve satisfying the equation we have there. Well, how can now, in the case of two-step nilpotent Lie groups, just recall how to construct those Lie groups. So a two-step nilpotent Lie group corresponds to a two-step nilpotent Lie algebra. And this is the following. So we have a vector space of dimension n equipped with a Lie bracket, and that is a bilinear and skew-symmetric map on the vector space, satisfying that once we have two vectors, we do the Lie bracket and then take another vector and repeat the Lie bracket. This is 0. Okay. So this is for the Lie algebra level, and the vector space could be identified also with the nilpotent Lie group by means of the exponential map. But this means that we can see both structures on the vector space of dimension n. So we have the vector space of dimension n. Once we have the Lie bracket, and we can see in terms of the Lie bracket as a two-step nilpotent Lie algebra, and also we can see this vector space with another operation, the product, which is written there, which is written in terms of the Lie bracket. So when we speak about a two-step nilpotent Lie group, this is a Lie group which as group is non-abelian. The abelian situation will be if the Lie bracket is 0, okay? But in the general case, we consider two-step nilpotent Lie groups which are non-abelian, okay? And once we have the setting, okay, we take a metric on the Lie algebra, and to translate this on the Lie group, we think that that this metric is translated by translation of on the left, okay, to every point. And this is the Riemannian manifold we will working with. Well, in the case of two-step nilpotent Lie groups, there is a natural decomposition given by taking the orthogonal sum of the center and the complementary subspace V. And once we have the Lie bracket, and we can define these maps GZ, JZ, which are orthogonal, okay, on the Lie algebra, at the Lie algebra level. Is right?
Yes.
Yes. Okay.
Yes.
Well. On the commutator of the Lie algebra is the subspace generated by the Lie brackets, and the center decomposes as the direct sum of the kernel of the map J, I define here, and the commutator. So those are the elements we will need to understand close two forms on two-step nilpotent Lie algebras. Or maybe two-step nilpotent Lie groups equipped with the left-invariant metric. But as usually, all the information we have when we say that we consider something which is left-invariant will be traduced at the Lie algebra level. That is why I am explaining what we need at the Lie algebra level. So we have this decomposition on the Lie algebra, which is the orthogonal decomposition of the center and the complementary subspace. And we have now also a decomposition of the center as a direct sum of the commutator and the kernel of the map J. Okay. Well, the restriction of J to the commutator is injective. As I said, the kernel of J is orthogonal to the commutator of the Lie algebra. And well, we have this result of Eberlein, which says that the subspace, the kernel of J and the commutator are commuting ideals in the Lie algebra. And so when we see what does it mean on the Lie group, it means that the exponential of the kernel of J is the Euclidean de Rham factor of the Lie group, and N is isometric to a Riemannian product of totally geodesic submanifolds, which is one is the corresponding to the exponential of the kernel of J, and the other one is a two-step nilpotent Lie group, which will be non-abelian, and is obtained from the rest that we have on the Lie algebra by using those decompositions. Okay. And another families, a way to distinguish the same families on the on two-step nilpotent Lie algebras is the following setting. So we say we will make use mostly of non-singular, but we say, well, that non-singular Lie algebras are those for which the maps JZ are non-singular for every element in the center. The other definition says, okay, if all maps JZ are singular, then we will say that the Lie algebra is singular, and one says that the Lie algebra is almost non-singular if we have maps JZ which are singular and we have other which are non-singular. This is essentially the way to see that. And one important example that we will talk about is that of H-type Lie algebras. So a two-step nilpotent Lie algebra with a metric is said of type 8 if the maps Jz satisfy the condition you are looking there, with where the square of Jz equals minus the norm square of the element set and the times the identity map. Okay, on V. The maps Jz are defined on the subspace V, which is, as I said, orthogonal to the center of the Lie algebra. And well, just to comment, the existence problem of Lie algebras of type 8 is naturally associated to the existence of representations of Clifford algebra. We will not make use of these representations, but we will have some results concerning H-type Lie algebras. Well, now go to the left-invariant to form. As we say, we wanted to study magnetic trajectories. That means that we need to see or to look for those Lorentz forces or skew-symmetric tensors of type 1,1 giving rise to closed-to form. If we think on the two form and we write down the condition to be closed, then we get the equation 1. Okay, for all elements U, V, double V in the Lie algebra, and if we decompose these equations, in terms of the composition of the Lie algebra, the center and the orthogonal subspace, we have two conditions, one written in terms of the center and the other one in terms of the elements of V. So the condition, as you see, the condition C1 evolve elements in the center. The projection of the elements of the center should be in the kernel of J. And the condition C2 is given for elements in the subspace V, but concern also the projection of the force on the center. Okay? And so we will work with those conditions.
So, Gabriela?
Yes.
There's no condition on the projection of F on V?
No.
No? Okay. Okay.
No, because here, if you look at the in one, okay, once you have the bracket, this goes to the center. So the part of V, yes, as V is orthogonal to the center, is this, implies this.
Okay. Okay.
So
thank you.
That's the question. Yes. And well, then we put something extra, which is to think in the following way the maps F. To think that F preserves the decomposition, or F interchanges the decomposition, interchange the subspace. Okay, so we will say that F is of type 1 if preserves the decomposition. That is, it sends the center to the center and V to V, and is of type 2 if sends the center to V and V to the center. Okay, so any skew-symmetric map will be decomposed in this way. So as a sum of a map which is F1 plus F2, there is the definition. And it is easy to see that the maps of the form of type 1, okay, satisfy trivially the condition 2, and the maps of type 2 trivially satisfy the condition C1. The first one we put in the previous slide. So now the point is the following. So to give rise to a closed-to form, F1, that is skew-symmetric map which preserves the decomposition should satisfy the condition C1, and F2 or a map of type 2 should satisfy the condition C2. So now the condition of giving rise to a closed-to form is decomposed for any of these other special types of skew-symmetric map into these two conditions. Well, then we have an equivalence, okay? So the skew-symmetric map F gives rise to a closed-to form if and only if the maps of type 1 and of type 2 satisfy F1 the condition C1 and F2 the condition C2, pardon, sorry. And in this setting, the two forms which are exact will correspond to, they are in the family of type 1, okay? They correspond with closed two forms which are given as the metric applied on maps JZ with Z in the center, okay? So actually they are always closed because they act only on the center, unless we have they act on V, especially when we have no Euclidean factor. This is trivial, okay, the condition. Well, it is possible to recognize these types of Lorentz forces, but not making use of the decomposition and of the metric. This is only making use of the two forms. This is important in some sense because this decomposition depends on the metric you are fixing. Because the vector space V depends on the metric. Okay, once you fix the metrics, then you have the orthogonal complement to the center. But we find that it is possible to think this decomposition in type 1 and type 2 and the condition 1 and the condition 2 in terms of the closed-to form. So closed-to form in terms of those families also can be written as type 1 or F type 2 depending on the center, only on the center. So for the first part, for the condition of the type 1, here the closed-to form is either non-degenerate or it is in the kernel of the omega. And for the type 2, the subspace, the center, is isotropic with respect to the omega, okay, to the closed-to form. So these are very distinguished conditions, and so we will see that we can say here that it is of type 1 or type 2 in terms of the closed-to forms. We worked with the skew-symmetric maps, but it was nice to find this condition which is independent of the metric, but only on the two form. Okay. And well, we find this result, which is important to determine which kind of Lorentz forces we can have on a two-step nilpotent Lie algebra. So if the dimension of the Lie algebra is greater than 3 times the dimension of the center, then there is no Lorentz force of type 2. This condition that the omega in the center and U equals 0 means that the Lorentz forces should be of type 1. And this means that this is a restriction, an algebraic restriction to the existence of Lorentz forces of type 2. And in particular, if we restrict to Lie algebras of type 8, then we prove that N admits a Lorentz force of type 2 if and only if N is the three-dimensional Heisenberg Lie algebra, the six-dimensional complex Heisenberg Lie algebra, or the seven-dimensional quaternionic Heisenberg algebra. That means from all Lie algebras of type 8, there are only 3 that could admit those kind of Lorentz forces or magnetic fields. Okay, close to forms. That was surprising, but it's a very strong restriction to the existence of two forms, or close to forms. Well, any question? Well, I did not find some kind of results in this direction, but if anyone could add something, it's welcome to speak about it.
Yeah, can I ask you a question?
Yes, please.
So it's mostly about the interpretation. I mean, the algebraic part makes perfect sense. I think you explained it very clearly. It's more about the interpretation. So so the Lorentz force, morally, this should be the exact three form, which is which corresponds to the exact vector field, which is the curl of the magnetic field, right?
Mm-hmm.
I think. So it's
in the cases we have the exact cases here, but this result is for the other cases.
Yeah, but
yes, it is possible.
I'm really trying to understand. So the Lorentz force is a vector field, right?
The Lorentz force is a vector field. Yes, but here, those are not well. As I think, I have no idea if they are left-invariant forces. You are considering the Killing vector?
I'm really trying to understand. That's why I'm asking you about the interpretation, because
well, here I am. Well, there is another setting that you can. Well, there are a lot about in the three-dimensional case where you define a product on the Lie group, and you can consider forces which are given by taking Killing vector fields, but these are not left-invariant.
Aha. Yeah.
Okay.
But so here's
it's another kind of forces that you see. It's more in the setting of the first on the general. I said at the beginning that you consider the cross product. Okay, this cross product can be generalized to a Lie group of dimension 3. Okay.
Yeah.
I spoke only in R3, but in dimension 3, you can define a cross product in dimension 3 and consider forces which are given if we change the magnetic field by a Killing vector field. And this is these are another kind of examples, but are not left-invariant, because Killing vector fields in two-step nilpotent groups are not left-invariant in general.
Okay, let me just understand this. Where does the Lorentz force live? What kind of object is it? Is it a vector field?
It's a 1-1 tensor. The Lorentz force in general. Okay, at the beginning.
1-1 tensor.
It's a 1-1 tensor. The Lorentz force is a 1-1 tensor. So in dimension 3, you can consider this 1-1 tensor as as acting as a cross product by a fixed tensor, as a cross product by a fixed vector field, which should be killing in most cases. But the Lorentz force is a one tensor in general.
Aha. So omega is the Lorentz force as far as we're concerned.
Omega is yes. If you look at the one tensor as a two form, it is equivalent. Omega is here a two form.
Aha. Okay. And now I understand. It's because in 3 dimensions, of course, you can dualize using the cross product. You can identify this two form with a vector field. And then we think of it as a vector field, right? But in general, you want to consider the abstract two form and call that the force.
Yes. Okay. Yeah.
Okay.
So
okay. Now
you can see either as Lorentz forces or as two forms. But Lorentz forces are also in the setting, in the 3-dimensional setting, is the force acting on the particle, and this is one tensor. The magnetic. The magnetic field is not so clear. The magnetic field is a corresponding two form.
Yeah, no, that's totally clear. Thank you.
Thank you. Welcome. Well, and as I said, what I say now is about the left-invariant, okay? Lorentz forces or left-invariant two forms on two-step nilpotent Lie groups, the algebra. So now to see something about the solution of this equation, of the magnetic equation, we can see that magnetic trajectories have constant velocity, but reparametrizations are no longer solutions. If we have an isometry that preserves the Lorentz force, then the composition of the isometry and the magnetic trajectory gives another magnetic trajectory. And if we do not know that, what we can do is to consider some reparametrization, but and to consider the composition of the isometry with the magnetic trajectory, and we will have a magnetic trajectory, but for another magnetic equation. So if we fix a Lorentz force and we have a magnetic trajectory gamma, the new magnetic trajectory will be the curve given by the composition of the isometry with the original magnetic trajectory will be a magnetic trajectory for a new force, which is the conjugation of the previous one. Okay, and if we write the magnetic equation at the Lie algebra level, as in the case of the geodesic equation in general on Lie groups, we have the equation you are reading there. Okay, where here for all people that know this equation, here it appears another term which involves the Lorentz force. Okay, and this makes this equation complicated. Also, if you see here, if f is 0, you get the equation for the geodesics. Okay. Well, by considering curves as exponentials of some special curves on the Lie algebra, we can see we get explicit the writing for the conditions on the curves. So we suppose we have a curve X on the vector space V and a curve Z on the vector space the center. So by the exponential, this gives you a curve on the Lie group. And so we will try to understand the corresponding equation for the magnetic trajectory. So if we write down the equations for the condition that should have this x and z, we will obtain the equation which is written as 2, okay, where in the first line we have all that is considered on the vector space V, and in the second line all the part for the center, okay. And so if you need the solutions, so you fix the Lorentz force, you decompose this into the projection on the vector space V and the center, and then you write down the corresponding equations for the curves x and z, and you need to get the solutions of equation 2, which are not easy. Well, if we write down for f in terms of the decomposition f1 and f2, where f1 is of type 1 and f2 is of type 2, then this is written in equation 3, okay, where instead of considering the projections on the center and on the orthogonal complement of the center V, we consider in terms of the composition F1 plus F2. And so we will give the solutions for the case F1. Okay, it is possible to get explicit solutions for cases F1. That is, for those Lorentz forces that preserve the decomposition C plus B. Well, and here you can see how are these solutions. The idea of the proof is very similar to that one in which Eberlein solved the geodesic equation on two-step nilpotent groups equipped with the left-invariant metric. Actually, the ideas are very similar, and you can write explicitly the solutions for those cases. Okay, that is Lorentz forces of type 2. That means Lorentz forces that will preserve the decomposition Z plus B. Yes. Well, here one needs to write down also the kernel of J to see how the map F is acting on V, and to make use of the eigenvalues and eigenspaces of the maps here, which are involved, but it is possible to find out this. We will see that in the Heisenberg situation. Well, just to exemplify in dimension 3, in the Heisenberg Lie algebra of dimension 3, and the corresponding Lie group of dimension 3, which is the Heisenberg Lie group. So we will recall that the Heisenberg Lie algebra of dimension 3 is spanned by 3 vectors, E1, E2, E3, satisfying that the Lie bracket of E1 and E2 is E3, and the other Lie brackets are 0. So the center is spanned by E3, and the vector space V, once we consider that this is an orthonormal basis, is spanned by E1 and E2. Well, the corresponding Lie group is modeled on R3 with the product you are looking there, and that means that the maps J, we have only one map, J only generated by a map, the J of A3, which is the skew-symmetric map in dimension 2. And in this case, the Euclidean factor is trivial. Okay, the kernel of the map J is 0. We have no Euclidean factor. And in this situation, we have both maps of type 1 and F of type 2. So any curve in H3 will be written as exponential of a curve on the Lie algebra, xt of E1 plus yt of E2 plus ct and E3. And well, xt and yt are in the subspace, are curves. We leave curves in the subspace V. Okay, spanned by E1 and E2. And so here, any at the Lie algebra level, the left-invariant Lorentz forces are represented by any matrix which is skew-symmetric in dimension in this dimension. This will give rise to a closed-to form always, and the case which correspond to exact Lorentz forces are those for which A and B are 0. Okay, so the exact case is for C non-zero and AB equals 0. And the exact case was solved by Epstein, Gornet, and Mast. It appears this year in Annals of Global Analysis and Geometry. As I said, it corresponds to this map, which are the J of CE3. Okay, J where the map J is defined before, and the corresponding equations are given in explicitly in this case. So here they look like in the geodesic situation, because here in the second line we have a 0 in the right side, and so the way to solve this is very similar to that one when you try to get the geodesics in the Heisenberg Lie curve. Okay, so in this case you have explicit expressions for the trajectories, for the magnetic trajectories, either with the initial condition is C or not, and you can see how are the forms of the corresponding solutions. So in this case, when the initial condition coincides with C, we get some lines, okay, with initial direction x0, y0, z0. And also there is interesting to ask if the trajectories could be closed, and they get a condition in terms of the energy level, but the energy level for them is given is not the square of the norm, but the usual norm of the vector in R3. Okay, so they give the condition for closed magnetic trajectories in terms of the norm of C, as you can see there. And well, in our work, we will work with the other non-exact magnetic fields and to see what are the solutions. So the first point for us was to write down those Lorentz forces, making use of the maps J set and the adjoint maps. And so they are determined by a vector u. The way to achieve this description is to consider the adjoint map and the transpose with the minus. Okay, in this way you have the skew-symmetric map. This is the skew-symmetric map actually of the adjoint map, of any adjoint map. And so you fix u, and you can write down in terms of u the magnetic equations which are there. And here, in comparison with the previous one, you see that you have something in the second line. And this is what complicates the computations. And we have something new. So by making use of the properties you spoke above, with making use of anisometry, we were able to go to the case where u is a multiple of the vector E2. And so we will give the solution in terms of u equals to b E2 for some b greater than 0. And let us write down explicitly the equations for this case. So we write down as previously the solution as where it's t, yt are the curves for those vectors. And so in each coordinate we have this equation. Okay, so we have 3 equations in x, y, and z, and these correspond to the magnetic trajectories. And so the idea to solve that is to solve the first one and then to put there the solutions in the other ones. So you can see the following. This is something that we get when we work with those equations. And so it is possible to write down that that this equation can be written in this way. Okay, so here it appears a new vector v1, which is a fixed vector, and it depends on the initial condition for the curve. Okay, so if we have a solution, a magnetic trajectory, then the coordinate x as a curve should satisfy this equation, where p of x is the polynomial we have there. And so if the x prime of t is greater than 0, then we have the following elliptic integral. Okay. For this other case, in this situation, we have to analyze the roots of this polynomial, and we can have 2 roots or 4 roots, and then we have the following expressions for the solutions of the equation. Here alpha 1 and alpha 2 are roots, and then we have phi as solution, which goes to the interval E1 and E2, which is given in terms of some integrals which converge in any case. And well, then we need the inverse, and then we have the solution of the equation 4. Even if we have the solution given in an interval, it is possible to join the intervals and to extend this to a periodic solution over R. Okay, so in the case of the function x, we will have a solution defined on R, and here you can see how we join the solution for the equation. And to get here is the other situation, and it is necessary to analyze how are the roots, but it is possible to find out all the solutions, possible solutions in terms of the roots of this previous equation. And here we have something like this, and well, written and explicitly we have the solutions written there, xt equals pt. Then you get, once you have the solution of x, you have the solution of y and z, also in terms of the previous one. Okay, you can see that y makes use of phi, that is of the solution x, and z makes use of both x, x prime, and y prime. Okay. This is in most of cases. In some particular cases, you also have lines through the identity. Okay. Well, something about the solution. The x of t is a bounded function. It is a periodic function under this condition. And if you have this another condition, then the trajectories are non-closed. And this is important when you have you try to go to see for closed magnetic trajectories on the compact spaces. So now we will try to say something about that. That is, we consider a lattice on the Heisenberg-Lie group, and do the quotient to get a compact Nil manifold. And here, when we say periodic, we are talking about lambda periodic curves, which are those curves satisfying the condition we have here. Say we fix an element lambda, and the condition of being periodic of period omega says that lambda times sigma of t equals sigma of t plus omega. Okay, and we will try to see if it is possible to have something like this for the magnetic trajectories in both cases. Well, the first case given studied by Epstein and Garnett was completely described for the exact Lorentz forces in this case, and they get they get their answer in terms of the energy, and comparing with the norm of this element C, which gives actually the exact Lorentz force. Okay, and they find also which are the periods. And in the other case, we have more work to do, but we find some condition which is given in the lemma. Okay, for having lambda periodic trajectory, the element lambda should satisfy a condition, and if we write down lambda as the exponential of v1 plus c1, then v1 should be in the kernel of f, okay, of the Lorentz force. If not, we cannot have the lambda periodic trajectory. And then in the case of we work with u equals E2, okay, on the Heisenberg-Lie algebra, we find the conditions for being lambda periodic explicitly, okay? And these are some of the references. And the first one is the the article of Epstein, Garnett, and Mast, and the second one concerns our work in progress. So thank you very much.
Okay. Thank you, Gabriela. Okay, then, are there any questions or remarks for Gabriela? I would like to know only, I know that the computations already in the three-dimensional Heisenberg are hard, according to what we've seen, but do you think you can solve some of them for higher dimensional Heisenberg groups?
No, they are not. That was the strong condition we get previously, that there are no of class 2. Okay, the only cases in which you have a class 2, that is, which sends the center to be, and okay, is in the Heisenberg of dimension 3, in the complex Heisenberg, that is real dimension 6, or the quaternionic of dimension 7.
Okay.
So, okay. For this, this only for the H types. I don't know in other non-singular, but
and there are computations already on this other on the complex Heisenberg or the quaternionic Heisenberg?
No. We are trying just to finish this and to go after that with those other cases. This was given by computation, okay, with computer, okay. So we make use of some program to get this elliptic integral.
Okay. Yes.
But there was surprising that they appear here something very different to the other cases, which are, if you look, the other equations are very similar to the geodesics one.
Yes.
And then the behavior is similar in some sense, that you say that you have something in terms of cosinus and sinus and so on. So, but nothing strange. And here, so you go from this. I don't know what is the situation if you because here we consider only type 2, but if you have something now, consider the sum, okay, the exact plus this one, and then to see what you obtain in this situation. This is another situation that we didn't solve.
Even in the three-dimensional case?
Even in the three-dimensional case, yes.
Okay. Okay. Well, very nice. I don't know. You have work to do.
I heard I think I don't know if Mauro. I think he's not here, but if he put in the computer a case, because at the beginning we put some numbers to get examples, and there were very strange graphics.
Okay, are there any other questions or remarks? If not, well, let's thank Gabriela again for her nice talk.
Thank you. Thank you, all of you.